Have you ever heard anyone say that the walls are as thin as paper? Or have you ever wondered why your voice echoes in an empty room? If you fill your room with objects or line your walls with foam, sound doesn't echo anymore. But why? What actually happens to the sound wave when the waves get absorbed? In this video, we will be exploring some of the components of sound-absorbing materials. Sound-absorbing material can come in a wide variety and are made of many different types of materials. This can range from inorganic man-made material like foam, organic material like wool and wood, or a hybrid of both. First, we'll explain how sound absorption is measured. There's a number called the sound absorption coefficient that is the ratio of the amount of sound energy that is released with the amount of energy that is absorbed. The closer the coefficient is to the number 1, the better the material is at absorbing sound. Here we have an example material that is commonly used to absorb sound in cars. It is called polyurethane foam, and although it can absorb sound at all ranges, it performs best at the range of 2,500 to 5,000 Hz, with a coefficient of 0.6 to 0.85. For reference, the lowest frequency humans can usually hear is around 16 Hz. People talking can range from 100 to 300 Hz, and car engines can range from 1,600 to 4,000 Hz. The highest frequency humans can hear is 20,000 Hz. The size and number of cavities in the material play a key role in the absorbance of sound. The smaller the cavities, the more sound will be absorbed because it will take longer for the sound waves to pass through the air cavities due to the higher friction with the molecules of air. Sometimes manufacturers add filler material such as silicone acrylics that can manipulate the size of the cavity so that it can absorb the frequency that are necessary for its purpose. Although the size of the pores and cavities and the number of pores and cavities play a large part in the sound absorption, the density of the material does too. Here's the equation for the theoretical relationship between the loss of sound waves with the structural and pore parameters of the fibrous sound absorbance material. This equation is way beyond the scope of what we know, so the important takeaway from the equation is that the density of the fiber or pore diameter is inversely proportional to the loss of sound waves at low frequencies. It also means that the loss of sound waves is proportional to the frequency of the wave, which means that there's more sound wave loss when the frequency of the sound is on the higher end of the low range spectrum and the density of the material is lower. If there is low loss of sound frequency, that means that the frequency of the sound is lower and the density of the material is higher. Soundproofing a room can be quite cumbersome because the more soundproof you want your room to be, the more material and the thicker the walls will need to be. In the past 2 decades, physicists and engineers have been working on experimenting with the artificial sheet of atoms called metamaterial that interacts with and manipulates both acoustics and optic waves. Through some research and experimentation, there are 2 known ways for the metasurface to be used for acoustic sound diffusion. These 2 ways are used to phase shift the sound waves so that the sound would diffuse. There is the reflective type acoustic metasurface, which is controlling the reflected sound waves. Then there's a transmission type acoustic metasurface, which is manipulation of the sound waves after the waves have been transmitted from the source. To summarize, the pore size, the density of the material, and the frequency of the sound waves all play a key role in what makes for a good sound absorption material. So next time you hear someone say, "I heard my neighbors yelling all night," these walls are paper thin. You can say that they can improve the walls with soundproofing and to be hopeful for the future because soon their walls will be as thin as paper and it will be soundproof. We hope you learned a little bit about soundproofing in the video. Soundproofing is quite a common thing nowadays and is quite useful for certain professions. If in the future you need to work with soundproofing materials, you will know how they work and how to use them.